Hello, calculus fans. Okay, so we're going to have a new topic now. We're going to talk about implicit differentiation. So up to this point, all of the functions we've run into can be described by expressing one variable in terms of another variable. So here's a couple of examples. You could have things like y equals tangent squared x, or y equals square root of x to the sixth plus x to the fifth plus x plus 1. The idea is that you can write y as a function just of x. So basically the right-hand side only has x's involved. The x's and y's aren't mixed together. So in general, we would say something like y is equal to f of x. Now, other times we have relationships like this. You could have 4x squared plus y squared is equal to 16. Here you can't really solve for y. Now we'll see later on you can sort of solve for y, and we'll see what happens when we do that. Now you should actually recognize this equation, at least the graph of this. This thing actually defines an ellipse. All right, so here's what the graph looks like. Looks like a stretched out circle. You have a major axis in the y direction, minor axis in the x direction. The real point, though, is that if you tried to solve for y, so you could do that here where you try to isolate the y. Once you get the y by itself and you take a square root, you're going to need to have this plus or minus in there. Now what that means is that you can't actually write this as a single function y equals f of x. That's kind of what we'd want to be able to do, but we can't. Well, it's not possible to do this, and you can know that from the graph because the graph fails the vertical line test. Any vertical line you draw will hit the graph in more than one place, so the graph of this thing cannot be described as a function. Now, we could, if we wanted to, we could graph the two halves separately. So if you graph them separately, they might look something like this, but this doesn't even really help us because we'd have to deal with them separately. And then there are other circumstances where you don't have any way of trying to solve for the y. Here's an example where you have almost no hope of trying to solve for y. I mean, this would be quite a mess and would be a pretty good achievement if you could actually solve for y. And then there's other equations where it really is pretty much impossible. So if it's impossible to try to solve for one of the variables, try to solve for y or even to solve for x, we're going to need a new technique in order to be able to find the derivative of y. The amazing thing is you don't actually have to solve for y to be able to find the derivative. So we're going to be describing the method of implicit differentiation. So when you have an equation like this, let's just say this one here, this implicitly defines y as a function of x, even though you don't have an explicit way of writing y as a function of x. So in a sense, everything that we've done up to this point, we've done explicit differentiation. Now we're going to be doing implicit differentiation. And we'll describe that next. Okay, that's all for now.